There is another talk about quantum key distribution in 5G and next generation networks by Sergiy.
Thank you. Good evening, everyone. My name is Sergiy Gnatyuk. I'm from National Aviation University, Kyiv, Ukraine, and today my speech is about modern technologies of quantum key distribution implementation in 5G and other next generation networks. Now I'm a professor in National Aviation University, and I am PhD and Doctor of Science in Cybersecurity and Professor in Computer Science in Ukraine. Also, I am the scientific advisor of a research laboratory on cybersecurity in aviation. And all my contact data you can see on this slide. So today we have already spoken about the cybersecurity, about confidentiality and privacy in 5G networks and other information communication technologies. And we have heard the speech about post-quantum cryptography in 5G. And my topic is related with this, but it is about quantum cryptography. Why quantum cryptography? Today, the implementation of different ICT services in critical infrastructure, in other information infrastructure of the state, in one hand, bring us the new abilities, new possibilities, new services, new networks, and some new models of business processes. But on the other hand, we have a lot of cybersecurity problems. For example, new threats, new vulnerabilities, new incidents, and so on. Traditionally, confidentiality and privacy in computer networks are ensured by cryptographical methods and means. But today we can see that computational power of the computers and other technologies is growing up, and we can see the threats from supercomputing, quantum computing, and others. In cryptography, the security is provided by the impossibility to solve some complicated task during some period of time, called polynomial time. Today, all cryptographical algorithms, symmetric and asymmetric, are based on some complicated mathematical tasks. For example, search in unsorted database, factorization, logarithms, and others. So when we are speaking about these problems, we imagine the possibilities of the attacker. And when we are creating the model of the security, the model of threats, model of attacker, we must analyze the potential ability and computational power of some attackers. But today, developing of quantum technologies, of quantum algorithms and computational systems causes them some threats to these attacks. And all up-to-date cryptography are under the threat. So what we can do? I think we have two ways of development. On one hand, we have post-quantum cryptography. The presentation of post-quantum cryptography was by Professor Yavish today in this room. And in other hand, we have quantum cryptography. What is the best and what technology must be implemented? This is very not simple questions, but I think that all these technologies are very important, and we must to combine and use some hybrid models. So when we are speaking about the quantum cryptography, firstly, we imagine the quantum key distribution. It's a main technology of quantum information security landscape. So on this slide, you can see the results of analysis a few years ago. I have analyzed most of all quantum technologies related with cybersecurity. As I have said, we have quantum key distribution, and other technologies are following quantum secure direct communication, quantum stream cipher, quantum secure secret sharing, quantum steganography. And the other, some protocols you can find on this slide with relation to some quantum physics postulates. You can find this on the down of this table. You can see the possibility to transform single bits, D-level systems, and quantum entanglement. The three basic technologies, and on these technologies, all modern quantum security systems are based. Traditionally, quantum key distribution consists of two parts. The equipment of Alice, equipment of Bob, and some connections. We have two connections. We have a secret channel, quantum channel, and open channel, classical channel. So the transmission of information, classical information coded in quantum states, is realized by quantum channel, and some additional procedures like authentication and maybe some procedures of identification of some users, of eavesdropping detection can be realized by a classical non-quantum channel. The example of BB84 protocol you can see on this slide. This is a very simple protocol and very old protocol. It was proposed by Bennett and Brassard in 1984. But this protocol is very important today because next we will look to some commercial quantum key distribution system, and the main quantum protocol in this system is BB84 protocol. Maybe not in original form, like more than 30 years ago, but BB84 protocol with some additional procedures like privacy amplification, additional coding, error coding, and so on. Another technology is quantum secure direct communication. It's very interesting direction of quantum technology in information security. We can compare quantum key distribution and quantum secure direct communication and define some advantages of quantum secure direct communication. Quantum key distribution cannot be it cannot be independent security system. It is only subsystem and it needs the subsystem of encryption. As a rule, in commercial systems, we can see the combination of quantum key distribution and, for example, AES encryption, maybe triple DES encryption, and others. And quantum secure direct communication technology proposes the secured data transmission via quantum channel without any cryptographical transformation. You can see the example of this technology. This is one of protocols, deterministic quantum secure direct communication protocol, called also Bostrom-Felbinger protocol and ping-pong protocol. And you can see two modes of this protocol work. In the first mode, Alice transmits the information to Bob, and in other mode, two users, Alice and Bob, are checking the channel and find the presence of eavesdropper in the channel. So, and they can switch from one mode to another during all the protocol. And you can see some coding operation in this table on this slide. So when users, when Alice wants to transmit some information, for example, information sequence 00, she must use some coding operation, the second row on this table, and second column, and use some operator for transforming. This is similar to some computer logic in traditional non-quantum systems. And physically, it will be the coding in some polarization state of qubit or other quantum system. For example, not only qubits can be used, QDs, Q3s, and others protocols. So today there are many quantum protocols, not only for qubits. Also, today we can see the development of standardization in quantum cryptography and quantum key distribution. There are some standards accepted by traditional organization, World and Europe organization in standardization. For example, International Telecommunication Union, ITU, has some standards on quantum safe cryptography of quantum key distribution, the framework of quantum key distribution, and other. Also, there are many protocols in the stage of draft, and we are waiting them in a near future. Also, today we can speak not only about quantum key distribution or maybe quantum secure direct communication. This is the whole ecosystem of quantum technologies, and you can see on this slide we have some vendors of quantum computing devices. We have vendors of quantum software, of quantum random number generation, quantum key distribution, some vendors with photon sources and photon detectors, of crypto systems and others. And most of all, you can see on this slide, this is some interconnected model of stakeholders in quantum cryptography and quantum communication market today. Firstly, we have speak about some threats from quantum computing and the vulnerabilities of existed cryptography. Why quantum computers are the threats? Today, there are many facts about successful quantum computers development, and today we have heard a lot of information from speakers about some cases of quantum computers developing and implementation in different spheres. For example, in cybersecurity and in cryptography, theoretically, quantum computer can be used too. Today, we have three types of quantum computers. You can see on this slide, these are quantum annular, analog quantum, and universal quantum. So the last model, the last type, this is the most powerful device, and potentially it can be used by attacker to make some damage and break crypto system. For example, today we know two quantum computing algorithms, Grover algorithm and Shor algorithm. These algorithms can be used to break some cryptographic systems. For example, Grover algorithm is a threat for symmetrical cryptography, and it can solve the task like an ordered database search. We have said about this task previously. Shor algorithm can be used in various directions. For example, for factorization, for logarithms. For example, in large discrete fields, and for elliptic curves tasks. And what we have? We have analyzed the current situation, and we can say that only for asymmetric or public key encryption there is the threat, because Shor algorithms provides exponential speed up, and well-known asymmetric algorithms like RSA, DSA, elliptic curves, Diffie-Hellman, and so on can be broken by universal quantum computing with realization of Shor algorithms. And two other domains of modern cryptography, for example, symmetric cryptography and hash functions, are not on the threat when we are speaking about the quantum computing and quantum algorithms. So in this table, you can see that, for example, symmetrical block cipher AES, yes, can be secured by larger key size using. So the same we can do for hash functions. For example, SHA, we can use larger output, and it will be secured against attacks based on quantum cryptography. When we are speaking about asymmetric cryptography, so I can say that the threat is actual, relevant, and post-quantum cryptography is very relevant in this direction. In this slide, you can see some calculations of the security of some crypto systems. You can see on the first column AES, TES, and some Ukrainian algorithms. First is post-Soviet algorithm GHOST 28147, and two implementations of our up-to-date standard in block cipher, Kalina. So we can see the size of block and quantum memory needed for attack. Sorry. Also, we can see some calculation of the security level against attacks on message block and key, two last columns. And from this table, we can declare that DES and GHOST are vulnerable to attacks based on quantum computer. Also, AES and Kalina with block size and key size 128 are vulnerable too, and key size must be larger to provide the security against these algorithms. Today, there are many quantum protocols and additional devices, additional systems on the market, and many vendors propose different solutions for critical infrastructure of some states and for common users. Let's look on these systems. The world leader in this direction is Switzerland company Gnatyuk, and this company during more than 20 years is leader on this market, and today they have proposed the fourth generation of some system of quantum key distribution and of quantum safe network security systems. You can see on this slide quantum key distribution systems, Cerberus and Clavis. These systems use in quantum part BB84 and other additional protocols like SARC or COW and AS encryption in traditional cryptography part. Also, they have proposed quantum safe network encryption system based on the quantum random number generation devices, and it provides the security of a quantum network. Also, very also many quantum key generation devices were proposed by Gnatyuk. You can see some of them on this slide. You can see devices for USB connection, for PCI, PCI Express, and some chips. And all these devices are based on some physical effects, and the developer has declared the high level of randomness of these systems. Also, you can see the quantum key generation chip of for IoT and critical infrastructure on this slide. Also, there are many single photon systems for generation, for detection, because it's very complicated subsystem and not simple task for engineers to provide the single photons pulses generation and detection in some different bases. It's very interesting but very complicated task. Also, virtual encryptor is presented by Gnatyuk, and it gives the possibility to build some virtual tunnels and provide encryption and the quantum safe security. Some new devices, few weeks ago, Gnatyuk has proposed ID cube detectors and Sergiy XGR system for scientific needs. This device is recommended to provide in laboratories for experimental study of some protocols realization, and also to simulate some additional procedures of pre and post processing in this system. Also, another vendors have proposed similar systems. For example, American company Magic Q Technology has proposed the first devices for quantum network more than 10 years ago, but today I can't find this vendor on this market. Also, Toshiba company proposed quantum key distribution system with symmetric encryption for critical information infrastructure protection. For example, it was deployed in the telemedicine system to provide the high security level of medical data in Great Britain and Japan. Also, Australian Labs Quintessence has proposed similar quantum key distribution device with quantum key distribution, and symmetric encryption. Our topic is about some implementation of QKD in 5G. In Ukraine, we have not 5G, but we have some test beds, and we are going to implement this technology next year. I hope this. When we are looking on some communication channels in 5G and in 4G, we can declare that in 5G we can divide we can define some layers, some slices of some critical users of some devices, for example, IoT, others technologies, for example, V2X technology, and so on. So there are many critical lines. There are many critical lines where quantum key distribution or other quantum technologies, for example, QRNG, can be implemented and allows to improve the security level. We have analyzed the current situation in 5G implementation in the world, and there are some interesting facts about the QKD implementation. For example, the first combination of 5G and QKD was in South Korea a few years ago. ID company and SK Telecom combined these technologies to provide the high cybersecurity level during the implementation of 5G networks in South Korea. You can see some layers and some principles of implementation on this slide. Different quantum random number generation were used in this system. Also, quantum key distribution was used to provide the cybersecurity between some basic station of 5G. Also, the cooperation of ID Gnatyuk and SK Telecom together with Samsung generated new results in communication, and today we have 2 generations of quantum smartphones. You can see that the first generation was presented in May of 2020, and this year in April the second generation of quantum smartphone, Samsung Galaxy, was proposed by these 3 companies. The base of the base of security of this smartphone is QRNG QRNG system, and it provides the stream encryption of the connection for subscribers. Also, British Telecom with ID Gnatyuk during the implementation of 5G in Great Britain deployed first practical quantum secure high-speed fiber network between their lab in Ipswich and between Cambridge. So the distance is more than 120 kilometers, and speed of data transmission is very high. Next example of implementation is Deutsche Telekom and ID Quantique proposed the quantum technologies to implement in telecom and IoT market of Germany. V2X technology is related with 5G, and there are many critical channels where QKD can be used. For example, communication between vehicles, communication between vehicles and customers, between other devices, and so on. So this is the part of critical infrastructure, and quantum key distribution and quantum random number generation can provide high cybersecurity level. There are many other quantum projects in the world. For example, a few years ago, it was a real revolution in quantum in China, and they have built a big project titled Quantum Science Satellite MODZ, and today this satellite allows to provide high-speed intercontinental quantum communication channel between Vienna, Austria, and Beijing, China. So the length of this channel is more than 7,400 kilometers, and this is the only one implementation of quantum technologies in the space today. Also, there are many examples of implementation in information infrastructure. For example, in Japan, in Tokyo, quantum key distribution is deployed in all city infrastructure, and you can see on this slide 3 levels of IT and communication in Tokyo, and one layer is quantum layer. You can see on the left corner of this slide. And also you can see the types of protocols. Quantum protocols, BB84, SARC04, and others were used in Tokyo. Also, some new technology was proposed, titled Quantum Safe IPVPN, and ID Quantique is working to implement this technology in quantum critical infrastructure. For example, in South Korea, all critical infrastructure protection system is based on quantum safe technologies. And there are other projects in Europe and in USA. For example, a few weeks ago, Unique Quantum Lab were opened in Czech Republic. Also, I know that the new communication channel and the first communication channel between two different states was deployed from Czech Republic to Poland. And also there are Some projects like ATOS system for combining the technologies, for example, big data, artificial intelligence, high performance computing and cybersecurity based on some quantum simulation platform. Also, today we have a lot of coding languages for quantum technologies, for quantum key distribution systems, quantum random generation. There are many coding languages, maybe some similar to traditional programming languages. You can see, for example, C#, Q#, and others. And next, I want to demonstrate some interesting results of my team. As I have said, I'm from National Aviation University, and we have cybersecurity R&D lab, and these are my young team. We have some interesting results in quantum cryptography. The first result is quantum deterministic protocol. This is improved protocol. It uses the QDs, particularly Q-threads. You can see on this picture on left corner the natural logarithmic information density, and we have studied these questions, and the most efficient in quantum cryptography are protocols not with qubits but with Q-threads. So we have proposed some protocol with Q-threads. And in these protocols, there are some problems. For example, the main problems of deterministic protocol is the impossibility to provide a high level of security. For example, quantum key distribution allows to provide theoretical information security level. In quantum secure direct communication, we can only provide asymptotic security level, and we need some additional procedures to improve the security level. Well-known approaches are based on some security amplification methods, for example, using reversible ternary matrices. But this approach is very slow, and it needs a lot of computational resources. We have proposed to generate treat pseudorandom sequences. After this, we can assess the randomness of these sequences and use these sequences instead of the matrices. And we have investigated these two approaches, and you can see that our approach provides protocol speed increasing at least in 1.52 time. And you can see on the picture in right side of this slide. So I have said about the randomness assessment. This is very important in cryptography problem too. And when we are using not bits but threads, we have not any tools to access the randomness. You can see on left corner some randomness tests well known. For example, NIST, STS, DieHard, and others. But all these tests are oriented only on to binary sequences, and we have had a lot problems with implementation these approaches to ternary sequences. And firstly, we have proposed the ternary quantum random number generator. You can see pseudocode of this generator on the right side of this slide. And after this, we have proposed new method for ternary sequences assessment. And you can see 6 stages of this method and structural and functional model of this method. After this, we have developed new software tool. This is like NIS STS tool for bits, and we have proposed treat STS tool for Q-treat and for quantum cryptography and maybe some applications with treats in traditional cryptography. The output data of this tool is a statistical portrait of the sequence. You can see on this slide, this is similar NIST STS. We can look on this portrait and we can make decision about the possibility or impossibility of using this sequence in cryptography. Also, in conclusion, few words about our plans for future. We are going to construct and implement the first Ukrainian national quantum cybersecurity system based on some our new and improved protocols of quantum key distribution, quantum random number generation. And in traditional cryptography part, we are going to use our new post-quantum standards, Ukrainian national standards, and additional procedures of authentication, privacy amplification, and error coding. Our laboratory are working not only in quantum cryptography. We have a lot of projects in cryptography, in programming, in artificial intelligence, in 5G and other network technologies. We have 2 main directions, scientific direction and some trainings from different categories of specialists. We are still open for cooperation. This is our site and all my contacts. Thank you very much for your attention. Maybe you have some questions.
Thank you. Thank you very much. So, yeah, 1 or 2 quick questions, because we're already late. If someone has one.
In practice, what's the real advantage of quantum key distribution if I always need a second authenticated channel?
Yes, quantum key distribution in practice needs this channel or maybe some additional procedures that can be used, and in this way channel cannot be used in these protocols. But in commercial quantum key distribution systems, there are 2 channels, yes. And quantum channel and classical channel for some authentication and maybe some additional information transferring between users.
If I have quantum secure traditional cryptography, so there are new algorithms that are quantum secure, what's the benefit of having real quantum photon-based security over the traditional but quantum safe cryptography?
Okay, thank you for your question. The benefit of the using quantum-based security methods is the first benefit is ability to detect eavesdropper in the channel, the first. And the second, for some types of protocols, it's ability to provide the absolute or theoretical and information security level. It's two main benefits.
Okay. Any more questions? Okay, thank you very much.
Thank you.
Sorry.